Okay, so you see here it's empty, but that will fill up over time. And if you can access Dropbox, then you can find it on the link that I posted. Maybe I'll post it again just in case.
So I think our third speaker of the afternoon, Claudia, she will begin to talk about higher Morita categories. Thank you, Claudia.
All right, so thank you very much. Thank you very much for organizing this wonderful conference. I'm very, very sad we can't meet in person in my beautiful home city. I was really looking forward to this. But nevertheless, we can at least see each other virtually, so that's fantastic. And thank you also for this really interesting combination of talks. I've really been enjoying it. So what I will be talking about today won't have that much to do with topological orders, but more with the higher structures part of the workshop. But it will combine several things that we have seen in several talks during the week. So this week we have seen, yesterday in particular, fusion categories and module categories for the fusion categories, braided for fusion categories. Of course, we've seen algebras and bimodules several times with semi-simplicity and so on. And then Davide Gaiotto mentioned a higher category of topological defects, which is desirable to understand topological orders within that. And we'll hear more about that later, I guess, by Theo. And just this morning, well, not this morning, but earlier today, we saw some fusion 2 categories or fusion n categories or multi-fusion higher categories. And a motivation, well, David explained to us that they should naturally live in certain higher categories we would like to call 2-vector, 3-vector. And just now in the previous talk, we saw what a seleptic 2 category is. So what's the goal of this talk is today is to explain a higher category setting, which in some sense combines all the above. So of course there will be different special cases where different elements of the things above will happen. And this higher category, well, is an interesting possible target for a topological field theory. So you can think of this as being some sort of like n-vects that we would like to have here, as in David's talk. And also this higher category isn't related, although I'm not entirely sure exactly how, but this is maybe something we'd like to learn, to Gaiotto and Johnson-Freyd's category of condensations, higher category of condensations. So another ingredient that's encoded in here is composing defects in some sort of a way. We'll see that that's like the pictures will be, look like we're just composing defects. And finally, I will comment on, I already mentioned that these higher categories you can think of as very natural targets for topological field theories. And I'll just make a couple of comments on this. So apologies to some of you who have seen me talk about this a couple of times, but it does fit quite naturally into the picture of this conference, and somehow, especially with the talks of today. Okay, so let's see. What's, should we start? So what is the thing that I will want to talk about? Maybe let's dive right in. What is the combining elements of a couple of these things above? Maybe let me highlight them. Which one is the highlighting? This one. So let's see, we'll have the fusion categories and the algebras and the fusion 2 categories. They're all somehow algebra objects in something, namely in vector spaces categories or 2 categories. And then we have the braided fusion categories, which I think was mentioned before as well, which are some so-called E2 algebras in categories. And then the third one is what we just saw in the previous talk, seleptic 2 categories. And it was written briefly on the slide that this is, you can think of as being an E3 algebra. in that case in 2 categories. So these are the 3 things that we will use: E1 algebras, E2 algebras, E3 algebras, and those will be the objects in the categories that we study. So that will be the category, the desired category. So this could be in vects, cat, well, k-linear categories, or maybe 2 categories, or other things. And I will talk a little bit more about what an EN algebra is later on. And so, first of all, we just have a category. What we need some morphisms. And these morphisms will be bimodules between these EN algebras, and that's also something I will explain. But actually, I said before, we actually want a higher category. So these are 1 morphisms. So we should also have a notion of morphism between morphisms. And since we have seen several examples of higher categories, so just 2 categories before, for example, I guess, unless there's a question, I won't explain this. But as 2 morphisms, what we will use is right, and here it depends for n equals 1. Here we will then use morphisms in vect, cat, cat, or whatever category we stick in, or for n equals 2 or higher, then 2 morphisms will be so-called bimodules or bimodules. Again, we will talk about what that could be later on. And then it goes on until n morphisms. And then we stick in even higher stuff. But let's stay with this for now.
So Claudia, can
yeah.
I ask a question? So that means your 1 morphism is a bimodule in a different category.
Yes. So here we have EN algebras in S. And the bimodules, I will explain precisely what I mean by bimodule. It will actually be which is an En-1 algebra. So it will be an E-1 algebra, which has a compatible action of the EN algebras that are the source and target.
Yeah, that's what I guessed. Okay, thank you.
Okay, so let's look at an example, because this can be a bit, take n equals 1 and vects. Well, my E1 algebras then are just algebras. And I will stop writing objects, 1 morphisms, 2 morphisms, and just kind of make a list. My morphisms will be bimodules. And my 2 morphisms will be homomorphisms. So this is the thing that we are quite familiar with. And here, we see various particular ones, namely the finite dimensional, semi-simple algebras, and then bimodules and homomorphisms. And this here was what David had called a 2-vect. Okay, so this will be my starting game, and all the rest will be a generalization of this. So maybe let's go back to David's talk. So I cheated a little bit, so I have a couple of things prepared here. And he had a really nice diagram here, which was the motivation for him to go up. So here, he said that he wanted as vects, he wanted vector spaces and linear maps. And he already built in a finite dimensionality. So maybe let me highlight this in some way, finite dimensional here. And then he said, well, we want to go up and get a 2-vect, which will be finite dimensional semi-simple algebras, finite dimensional bimodules, and bimodule maps. Yeah, so I should have added finite dimensional here. So that's exactly this thing that I wrote on the right. And again, if you note, we already have quite a lot of finite dimensionality built in. And the same on the right-hand side, he reformulated this via finite dimensional modules. And again, we have a lot of finite dimensionality, well, at least there. And in the 3-vect, what we have here is multi-fusion category. And again, finite semi-simple and semi-simple. So in his categories there's already quite a lot of finite dimensionality built in. So the thing that we will want to look at, so this is in David's talk. The thing we will want to look at are natural higher categories where this sits inside, okay? So we will, if you look, we start with just arbitrary vect, not finite dimensional vect. And then our algebras and bimodules do not have any conditions, not the semi-simplicity. And similarly, when we get to the next step, we will also have a version where we have monoidal categories in it, but not necessarily these strong finiteness conditions that are here. So you do need some finiteness conditions, but not in that generality. So S equals cat K. Where here I want to be a little bit agnostic, so there's quite fun. Not much needed. One could take presentable categories, for example. Then we have monoidal cats or tensor cats, depending on how you define tensor cats. And then we have bimodule categories. And then we have homomorphisms. So this would be the natural place where this sits inside. But as you see here, we have our bimodule factors. So these are our homomorphisms, but we also have natural transformations. So actually here we can go even further. We also have our natural transformations. And in here is this 3-vect from David's talk. So the things we will look at are common generalizations of these two cases. Questions so far? All right. Great. So let's go back to the heuristic picture. We had objects will be n algebras, morphisms will be bimodules, and then it depends on whether n equals 1 or higher. So why would we care? Well, we already saw somehow in relation with other talks that this makes sense to look at these things. Another motivation maybe is that, well, from a TFT background, you might just want to have such a hierarchy of n vector spaces where you can actually then compute things. So, right. Let's see, from the cobordism hypothesis point of view. I didn't give this a name yet. I will call these, let me add this here. This is called alg_n of S. So the n is the same n as here. That's important. So now we look at symmetric monoidal functors into this alg_n. So this is, by the cobordism hypothesis, the same as an n-dualizable object in alg_n. And then And this is basically the main theorem that I will mention today, is that one can show directly that every object, so i.e. every En algebra, is n-dualizable in AlgM. Of course, this is somehow, so first of all, two remarks. So first of all, this the values of the TFT can be computed by factorization homology. And actually, you've seen some examples of factorization homology being computed in the previous talks, namely certain centers are just basically a factorization homology, if you understand it in the right way. And the second remark is that, of course, let's go back up and look at our AlgN. So if you look here, the N was 1, and we were looking at not only a 1 category, but a 2 category. And here, my N was also 1, but we were looking at even a 3 category. So for the purposes of somehow understanding for this right-hand side here, this here, actually is an N plus K. So where this here is a K category. And so this is actually something that Theo Johnson-Freyd and I proved or constructed some years ago. Okay, so this using previous work, now I'm running out of space. I should have moved this a little bit down. Apologize. So there are some subtleties here that I won't go into that I'm happy to talk about privately, but I don't think there's much point here to talk about this. Okay, so we want more dualizability in general for invariance. And this is here, the finiteness conditions. Such as semi-simplicity or fusion up here. At least they become sufficient conditions. For most situations, we actually don't know necessary conditions. All right. So I thought this is, because this is an iPad talk, I can actually use that I can have pretty pictures very easily. So I actually want to get to the part where I get to show you pretty pictures. So maybe the next thing is the full statement of the theorem that I would like to explain to you, and then we'll actually talk about what this AlgM is in more detail. So this is just a bit of a stronger version of the theorem from above. So we have an actual higher category. So this is an M plus K category. So when I say N category, I usually mean an infinity N category, but again, this is not the place to talk about these technicalities. And in here, we have something even stronger than just that every object is n-dualizable. Namely, we have that every object has a dual and every morphism has a left and right adjoint for K morphisms, for K less than N. Okay. Great. So what's this algem? So I just wanted you guys to have this so you can come back up and scroll back up if you want to. All right. So the definition of algem of S uses factorization algebras. So what's that? A factorization algebra with values in S on, and I will actually make my life a little bit easier. I won't give you the full definition today. I will just give you the definition for Rm. And it doesn't really matter, the definition is the same, but so it is a precaucheif going from open sets in Rm, and we will actually to S, and we will usually actually only think about disks, together with, for every disjoint union of disks sitting inside a bigger one, we have a structure map So here we're really using that this should be a symmetric monoidal category. Actually, it will be an infinity category, but again, feel free to ignore that. So think of the category of categories or vector spaces or chain complexes, such that, well, we have a coherence condition. So if I have a big open set and intermediate ones, well, I could also include little ones in here. And whether I include the little ones in the middle one and then the middle one and the big one, or right away, that is the same. Well, it commutes. And we have a gluing condition, which I will phrase in 2 steps. I will actually only talk about the one that will be relevant for us. The other one will actually not be very relevant for us. So if I have my map from U1 so I will want to take a disjoint union, and this receives a map from the tensor product of the U and V's, and this should be an equivalence. And then there's another gluing condition. Okay. All right, so this is a long definition. But the point is that we can draw these pretty pictures. So the first example would be to take an algebra, and then I construct, so this will be unital and associative. I construct factorization algebra FA on R, which I will only tell you what it does on intervals, and then you can think about why this is enough. To an interval, I will just assign A. Okay, so if I take another interval here, I will also assign A. And now if I take a big interval, this will also get assigned A. So for later purposes, they should all be the same color, but I just want to be very clear here. So we need to get a map like this, and this will just be the multiplication. So this will be the F for these intervals. So algebras are examples. And similarly, E2 algebras, En algebras are also examples. Wrong color. And indeed, there's actually a very nice proposition or theorem by Jacob Lurie, namely that if you take locally constant factorization algebras on Rn. And so let me tell you what that is. This says that if I have an inclusion of disks, then my structure map is an equivalence. Okay, so that's a usual local constancy condition. And this here is actually equivalent to En algebras. Okay, so we saw somehow one direction for n equals 1 above. That was this example of the algebra, and this works more generally. So why do I like this? I like this because the left-hand side is a very geometric thing. So here, I will just draw the underlying Rn. So I just have my f sitting on my Rn. Okay, so this is a geometric thing that I will want to manipulate. So if I draw a picture like this, I will always want it to be locally constant. And then there's so this will be the thing that we will exploit to build our objects. Okay, so what will be our morphism? So these, maybe I should use a different color again. These will be objects of algebra. So what about morphisms? And I will show you a picture. So my morphism, I will depict in a way like this. So this will be a factorization algebra again, factorization algebra on R2. In that case, I mean, I'm drawing R2, of course, now. This is on n in general. But now for n equals 2, such that, and so on. For n equals 2, the picture is below. And so it's not locally constant anymore, but it's still constructible. So what does that mean? So here now, before I was allowing any inclusion of disks in my condition, up here, any inclusion of disks, and I wanted them to be sent to the same thing. Whereas now here, I only allow certain inclusions of disks. So if, for example, if I take these two, then I have a structure map and these should be equivalent. So let me just draw this as a little equivalent here. I don't want to specify too much. On the other side, if I look at this one here, well, this will also be something like this. And maybe this will also be an equivalence. And maybe I also want to show you that, well, if we have inclusions like this, that's where you start seeing the E2 algebra showing up. Those are pictures you might have seen before. Okay, so where's the bimodule? The bimodule will be something like this in the middle. Okay, so this will be the bimodule. And how does something act on this? Well, I just take something on this side and then include it. Oh, that should be black. And I include it into a bigger one like this. So that's how my module action works. And the same for the right-hand side for the bed. Okay, so little blue into big blue. This is an equivalence. And then also f of little red into big red is an equivalence. And f of little black, so that has a little line, into a big black is an equivalence. So these are these constructible things. If you want a full, more precise definition, I'm happy to talk about that later. Okay, so these are morphisms and objects in bimodules. And let me just show you a picture of the next step. Namely, that would be something like this. So these are now two morphisms. Oh, I should have said maybe how do I extract from a picture like this the source and the target? Well, the source will just be restrict to the blue stuff, and the target will be restrict to the red stuff. And so for such a two-morphism now, where are my, what does this encode now? Well, I again have an R here, which you can think of as an E2 algebra. Here I will have my S on the other side, which will be an E2 algebra. And then I have one bimodule down here, A, but now I need another color, purple, so there will be another bimodule, B. And notice, and this is already visible in the picture above, actually. I should have mentioned this above. Maybe let me draw it in the bottom picture. Notice that if you take two little disks, two opens that intersect here and include it into a big one like that, you also have a multiplication. This will also be a multiplicative associative structure. So this will be actually an E1 algebra. The same is true here above as well. I forgot to say that here. Bimodule, which is an E1 algebra. Okay, so our bimodules eat up one direction in some sense. So they eat up this direction, but they still have an E1 algebra structure in the other direction. That's how you should read these pictures. Okay, and then we're left in the middle with something new, namely this will be now the bimodule of bimodules. All right, so these pictures are quite useful. And let me show you very briefly how to compose, because that's something that hopefully will look familiar in terms of defects. So this is how composition works. I will also copy it over. So the left-hand picture, of course, is for morphism, for the case n equals 1. So this is n equals 1, and then this here is n equals 2. So I'm just, basically what we're doing is we're collapsing these two defects, so just collapsing them together to get something in the middle. And what this corresponds to is a relative tensor product of modules. Okay. So this is a composition of one morphisms. All right, are there any questions at this point before we actually go in the last 10 minutes to showing some pictures of how we would like to prove a theorem like this? Okay, great. All right, so let's go back. What's the theorem that we want to prove? So this is this bottom part, the object 1 morphisms up to n morphisms, and I can draw them as pictures. So we would like to show this theorem. Oh, sorry about that. And in particular, today we will talk about the second statement. The second statement because those are the pictures that we were drawing before for n equals 2. So then we're only left with k equals 1. So it simplifies quite a bit. Idea of proof. Okay, so why is this picture this theorem interesting? As we said, we want to get these dualizability conditions, and having a left and a right adjoint. Well, for the dualizability, we only want certain morphisms to have left or right adjoints, but here we actually have it for all of them. So what does it mean? I will just show that a particular one morphism has a left adjoint. So let's take this R acting on A, which is also acted on by S. The guy from above, this is a one morphism, this is a generic one morphism, has a left adjoint. I.e., what does that mean? Maybe let's write it down for L and R. Well, that's bad. This is called A. Okay. We want a B, which is acted on. This should now go in the other direction. This should be an SR module, such that, now I have to use my cheat sheet. This bold R, well, because this will be the right adjoint, and this is bold L, because this will be the left adjoint, and now we want the composition of these. We want the identity. And now I always get the directions wrong because they switch later on. We want this and that. Is that correct, or did I get the directions wrong? So we want two morphisms as such. So this will be the co-unit, and this will be the unit. Okay. And then there's a certain snake relation, which I don't want to draw out now, because you will see it actually appear in a moment. Okay, so let's go back to our picture here. This was the picture that we started with. And this is the guy that we want to construct an adjoint for. Okay, so this is my R, and I want to construct the left adjoint. So I want to use this thing. So this is a geometric thing. And what I want to do is I want to use a diffeomorphism of the underlying space. So this is an F, a factorization algebra on, well, in this case, R2. And I will use a map from R2 to R2. And one nice thing about factorization algebras I can do is I can push them forward. So this F, maybe I should have called this F R A S. This is this factorization algebra. I just want to have one symbol for the whole thing. And I want to push forward my F along this. So what I will do is the following thing. I want to deform this top thing. Maybe let me paste this again. I want to take this, and what I want to do is I want to pull this up and over, and all the way to the bottom. Okay. So if I had a better illustrating tool, I would show you that like I'm pulling it up and down. So this will give me a diffeomorphism of R2 to R2. And the image will be exactly this here. So the pushed forward factorization algebra is this guy. Okay. So what do I mean by this? I mean, this is a factorization algebra. This is on R2 again. And what I mean is that if I evaluate at something that's in the blue, I will take my R. Everywhere here it evaluates to R. And on the inside, it evaluates to S. And any disk that touches the black, that will evaluate to A. Okay. So that's a factorization algebra. Fine. This now, we started with a one morphism. This is a one morphism. This is not an object, one morphism, K morphism in AlgM. So that's weird. We constructed something that is not in my AlgM, but it's still a factorization algebra. That's an okay thing to do. But I can construct a two-morphism out of this. So this will give us a two-morphism by pushing forward along another thing. Namely now, something like this. So what I did was I squished it together. So squish this together. This is similar to this is similar to our composition maps from above. Okay, and so my claim is that this will be a co-unit of the adjunction. Okay, so let me try to convince you with one picture why this is true. Picture proof. So I also need to get a unit, and I do a similar thing. So the thing that we had now was this top part here. And we could have done a similar thing by just bending the other way to get this bottom part over there. And the cool thing is that these actually fit together in a really nice way. So notice again, this is not happening in AlGen. This is happening before this collapse. But what is very pretty now is that from this big part, well, you can, I mean, on the underlying spaces, you have a diffeomorphism that just pulls them apart. I mean, this is the usual snake type argument that you really just have an identity. And the somehow neat fact is that now if you start collapsing, whether you collapse these first and then compose, or whether you just take the big composition here and then collapse, you will always get this part over there. So that's somehow the picture proof that this construction that we were doing really is an adjoint. So of course you can now go back and think about what this means for E2 algebra, say for braided monoidal categories. And I want to end this by saying this is worked out in detail for braided monoidal categories. So E2 algebras in CAT by Brashier, Jordan, and Snyder. And there they also talk about conditions, what these braided monoidal categories have to actually then also have higher dualizability, say 3 or 4 dualizability. And that's where fusion conditions reappear again. Okay, I think I'm out of time, so I think I will stop here.
Okay. Thanks for your time.
Right.
Initial
Can I ask? Yeah, so I know that you can answer this because I saw it flash very quickly on the screen. Can you talk a little bit about what's happening with the framings? It seems that when you do your twisting, the framing gets all screwed up.
Yes, exactly. So this is something that, of course, I couldn't tell you in detail now. But if we look a little bit more closely what happens here in this like move up and over, I want to tell, I mean, why would I want to think about having a framing on this thing? I have my little arrow here, yes. So you can think of, I'll just put it in here, because I want to think of this blue part as being an E2 algebra. So what's an E2 algebra? Another way of thinking about this is that I have two multiplications. And I mean, they're isomorphic, and this isomorphism is exactly the braiding. And so you can think of these two multiplications as going in one direction and the other one. So I want to think of this, say for braided monoidal categories, this is the monoidal structure. And this one, well, it's also a monoidal structure, but you can also think about it a little bit as if this were the braiding. And so what happens now is I want to understand what this dual really is, the adjoint really is. And so for doing this, I have to keep track of what happens to these the multiplications as I do my moving up and over. So you see, I mean, by up and bending, of course, I have to take, if I just follow what this vertical arrow does, I will have to make it follow my black line here. So what happens is we get this very funny twisted thing here. This part here, and that's exactly where you see the adjoint. So this thing that I just outlined in black, that will be the adjoint. So if we think of this left-hand thing as being A as an RS module, what's happening here is that, I mean, I can also draw my arrow on this picture. So what I will actually have here is my A op, the opposite. And then I want to still have this as an S, an R module. But a priori, the opposite would only be acted on by S op. And so what this here is doing is that it allows you to act, but this uses the braiding. And the same here, but this uses the braiding. So that's something you have to be a bit careful about, because you have to remember how it uses the braiding. And whether you turn left or turn right, I mean, makes a difference.